Thanks for the introduction. Yeah, hi everybody, I'm Ed. I'm going to be doing something that I don't normally get to do when I give this talk. I'm going to be talking about our compiler, BQSKit. What I don't normally do is talk about some of the bad things about it. Normally when I'm up here talking to an audience, I'm talking about all the good things. But today is going to be the good and then some of the bad. And there's nothing ugly here, but we're going to talk about the future at the very end. All kind of in a very short 25 minutes. So let's get on with it. So the Berkeley Quantum Synthesis Toolkit, BQSKit, is a powerful and portable quantum compiling framework. It gracefully handles every gate set and architecture. This is what I mean when I say portable. It has specialized pipelines for widely used chips. And we've used it to generate resource efficient circuits for a variety of different definitions of resource and efficiency. And we have error mitigation capabilities, and all of this has come together to enable effective algorithm and hardware design exploration. There's a link here. There will be more links throughout the talk that show up, but this is all just going to bqskit.lbl.gov, which is a launch pad for everything that is BQSKit. You can get to our GitHub there. Everything that we do is public. You can get to our code and our documentation from there. We have many different papers. A lot of this has been enabled by NERSC, so I have to say thank you, and I will say that multiple times throughout the talk, pointing out just how awesome they have been in supporting us with this project. And the software has over 500,000 downloads at this point, with users across the world in industry and in academia. This has turnkey functionality that works everywhere. So on Python 3.9 and above, Windows, Mac, and Linux, you can just do pip install BQSKit. And this goes from laptop to supercomputer being downstairs that a lot of you just came back from Perlmutter. It's worked on that plenty of times. And if you want to use this off the shelf, which works for a variety of use cases, you can just do import BQSKit, bqskit.compile, and what goes in is anything that you have, and what comes out is anything that you want. That's what I really mean when I say portable. It really can handle any gate set, any architecture, qubits, qdits. You can even do synthesis. You can just plug a unitary in, and we'll expand on these concepts in a bit. Also, if you have any questions at any point, feel free to just cut me off and ask a question. So all of this is built on top of this concept of instantiation. This is how we get this portability out of BQSKit. The process of instantiation is taking a parameterized quantum circuit, this thing on the left here, and finding the values to that circuit that make it most closely implement something, minimize some cost function, whatever it is. It's really a general definition of find values for this parameterized quantum circuit that make it do something you want to do. And this is used all over the quantum space, but in the compilation, it's a very, very powerful primitive that we build on. And we solve this typically numerically by employing a numerical optimization routine with a cost function that's given here. And why is this so powerful? Well, it's because we can separate out function of a circuit from the structure. What do I mean by that? Well, the function of a circuit is what does the circuit do? This is the mathematical representation, maybe the unitary, maybe the Hamiltonian. What is that circuit doing? This is the function of a circuit. From the structure, how does it accomplish, how does it implement that function? This is the type and placements of gates in the circuit, or a parameterized quantum circuit, circuit structure, things like that. What we can do with this is we can take a circuit, an instantiated circuit that's an input, separate out the function and structure. We can vary one or the other, maybe in some special cases, vary both of them, and use instantiation to hopefully bring it back to something that we want that's better. So we use this really at the origin of BQSKit is synthesis, this thing called bottom-up synthesis that we do. When I say synthesis here, I mean the process of taking a unitary matrix or another high-level description of a circuit function and finding a circuit that implements that function. And so the way we do this with instantiation is more or less take a guess at a circuit structure and instantiate it. If that works, great. Maybe you're lucky on your first try. If it doesn't work, guess again. There's obviously more structured ways that we accomplish this. The most canonical way is Q-search, where we build up this tree of circuit structures, starting with very few gates at the root, and we add gates as we go deeper into this circuit structure, or circuit tree. And as we pass over a node, we instantiate it, and we use something like A* or another search algorithm to find a solution. And once you instantiate a circuit that has an error that you're happy with, you found a solution. And if your search is good enough, like A* is, you can find really, really good solutions this way. We can also do more advanced things with instantiation. We can transform circuits rather than building them up. We can take something, make changes to the structure of the circuit using instantiation iteratively as we go, depending on the algorithm, and eventually end up with something that is either optimized or more transformed. An example of this is gate deletion. So in this example, we're going to optimize a circuit. I know optimization is an overloaded term. Even in my talk alone, I've used it a few different ways. What I mean here is find an equivalent implementation of this circuit that has fewer gates, but does the exact same thing. We're going to start in this top left. This is our input circuit. We're going to pick a gate, any gate, and remove it from the circuit. That's going from the top left to the top right. Now, that's not normally okay. You can't just do that. You can't just remove gates from circuits. But what you can do is take that top right circuit and reinstantiate the parameters to that circuit in an attempt to accommodate the lost gate. This is going from the top right to the bottom right. And this works in a surprising number of cases. A lot of the inputs that we have from circuit generators are very suboptimal. And we can accept the result in a lot of cases. The error that you get at the very end is good enough for what you want. Sometimes you have to reject those. Sometimes you can't remove that gate. It's very crucial to the algorithm. So you have to have the ability to reject and go back to where you start. And you repeat this process. You select different gates, you repeat this process, and you end up with a highly optimized circuit from where you started. There's a couple things I want to point out here. This process is extremely portable and flexible. Note that there's no labels on any of these gates. Maybe those are C0s, maybe they're not. Maybe these are QDITs. It doesn't really matter. As long as we can represent these circuits mathematically, then we can do instantiation over it. As long as we can represent it mathematically, which in quantum computing is pretty much every program, then you can optimize it this way and you can use this instantiation engine and solve it this way. Right? These could be QDITs, these could be any gates. It's also very effective due to global transformation. So what I mean here is that the entire circuit is transforming. Every parameter in the circuit is changing in an attempt to accommodate that lost gate. This is as opposed to traditional based or template based, rule based optimizations where there's a very fixed scope that you're looking in the circuit or you're looking for very specific templates. This can find very non-intuitive, non-human optimizations for very specific rewrites. And as a result, it's very effective. We're able to optimize a lot this way. So instantiation is this primitive inside of BQSKit. It's at the bottom of everything that we do. On the left here, I have an example. This is just an example of all the things that we can do in BQSKit. On the left here, we have circuit synthesis. So we have a variety of different synthesis algorithms for different use cases. And on the right, we have circuit transformations. We can do things like retargeting, gate deletion. We can do template substitution and circuit resizing. The core idea here is that we can do a lot, and instantiation is really underneath all of it. We can also scale to thousands of qubits with our compiler through this method of partitioning. So we can take partitions, another overloaded term. So what I mean here is take a very large circuit. In this example, it's just 5 qubits, but we can group together adjacent gates into blocks of fixed width. So in this example, this 5 qubit circuit is partitioned into 3 3-qubit blocks. Then we can recursively apply our algorithms on those blocks. So this overcomes the exponential scaling of numerical instantiation, but it does introduce a trade-off. This restricts the global view that I just introduced in a couple slides ago. As you increase the block size, you're going to get better quality of results because your scope of instantiation is larger. As you decrease the block size, you're going to get faster results. Compile times are going to go down. One other cool thing about this is that this creates an extremely parallel workflow. If you have 1 million qubits and you have 1 million billion blocks, and for some reason you have underneath you a supercomputer with 1 million billion nodes, say Perlmutter, then you can distribute all of your algorithms, all of your blocks, each node, run everything in parallel. This is an embarrassingly parallel problem, and then collect the results. This is all push button in BQSKit. So there's a distribution mechanism in BQSKit. You can distribute this over a supercomputer and run it this way. One other cool thing that we get from this is that we can verify our transformations. If you have a 4-qubit circuit, you do some compilation, you do some transformation on it, it's pretty easy to say what you ended up with versus what you started with are the same. But if you have 1,000 qubits, it's not so easy to do that. But because we compile by partitioning circuits, we can actually add up the errors of the individual blocks. And using the triangle inequality, we can get an upper bound of the error of a transformation. And we can use this analysis to say that, or verify that our transformation was correct, that we're not just going off into la la land, that what we're doing is actually keeping the semantics of the program that we started with the same. All of this comes together in Biscuit to produce what we call workflows. Workflows perform end-to-end compilation tasks, and we have things in Biscuit that do everything. We have resource optimization, we have mapping and routing, we can do transpilation, we have error mitigation and fault-tolerant compilation, design exploration, these are newer things. We also have advanced capabilities in Biscuit. Dynamic circuit synthesis is also a newer one. Performance and quality scaling, hardware portability, and we have some new advanced methods for circuit approximations. Fortunately, I don't have too much time to talk about each one of these individually. This slide here on the right is very much outdated data. This is a few years old at this point. PAM, which is our state-of-the-art method, which is now part of Biscuit. This graph, the purpose of it showing here is just to say, hey, look, what we're doing here is very competitive with commercial compilers. Okay. That was the good. Now a little bit about the bad. I don't normally get to do this, but the reason I'm doing it here is because the solution will come. So Biscuit is portable, but batteries are not included. So it's not necessarily important to read the code, but it's important to see the length of it. This is the definition of a U3 gate, a general single qubit unitary gate in Biscuit. So you can define a new gate. Say you have a new emerging gate that you want to define and work with. This is what you're looking at implementing. It really isn't that much, but on closer thought, you have to figure out the boilerplate. Now, I've written many gates in Biscuit. For me, it's not that hard. But for a new user, they have to learn the library. They have to learn the boilerplate. They have to learn what these things mean. There's a little bit of an obstacle there. Now you also have to implement a unitary evaluation. But you don't just have to implement the unitary evaluation. You have to do so efficiently, in a way that is in a programmatic way as well. Second, most importantly, you have to also implement the gradient calculation. And matrix calculus can get very funky at times, and it's because a matrix does not commute with its derivative, and this can create some very difficult to debug errors. To give you an example, a squared, the derivative is not equal to 2a dA. It's a dA plus daa. And these kinds of little funky things can really be difficult for users who are not familiar with this to debug, because these bugs don't show up so clearly. So this gets portable, batteries are not included. Additionally, preface to this data, BQSKit and Ticket are amazing pieces of software. This data is very old. Everyone on this has advanced a lot since this data has been published. This is now like 3 years old. The point here is to talk bad about Biscuit. Now, what I want to show here is that our method PAM is a very valuable method. It's comparable with commercial compilers, and it's very useful to try out. But look at these runtimes. Look at this short computation. We're talking 10,000 seconds to do compilation, where BQSKit and Ticket are on the order of 100 seconds. This is costly, especially for people who are doing repetitive development and recompiling multiple times. Sitting and waiting 10,000 seconds just because you hit enter on a Jupyter Notebook cell, that hurts. So instantiation-based compilation, it's high quality, but it can be expensive. That was the bad. The future. So OpenQDit is a new software package that we are working on. It is very much a work in progress, but it is lending itself to extensible and accelerated numerical quantum compilation and helping to solve some of the problems with Biscuit that I just mentioned. I'm going to briefly go over OpenQDit. Hopefully I have enough time. So OpenQDit, it's a extensible and accelerated quantum information library. It has highly optimized low-level quantum software features, mainly a versatile abstract representation for quantum programs as circuits with accelerated numerical subroutines. This is a QR code to our GitHub page. It's very bare bones right now, but I encourage you to take a look at it, star it, keep an eye on it. And there's another thing here that's not really going to be talked about, but a lot of this is working towards, as a goal of mine, safety and interoperability in the software ecosystem. We introduced this language that we have with this system called the QGL that I'll introduce formally in the next slide, but just to give you an example of it, a sneak peek, all of that U3 stuff on the previous 2 slides ago, that's this. In this OpenQDit, all you have to do is define your gates as you would write them in your mathematical notebook or in your notebook. Write them down on paper. There's no difference here. Greek letters even are supported in this. You write it down as if you were writing it. What you get from that is everything. You can take these expressions and compose them to build new expressions. You can evaluate them for their unitaries. You can evaluate them for their gradients. You can even do equality testing over them symbolically. There's a lot more that you can do. But the cool thing is that it's extremely fast. Everything here is highly accelerated, and I'll show some numbers here in a second. This, by the way, is faster than our hand-optimized U3 that we've built in BQSKit and used for many years. So we have this Qt language that we propose as part of this package. Here's a couple examples of what that syntax might look like. You can define constant gates. There's a C0, very simply. You just define the matrix. Here's a parameterized gate. You can also do Qtits, hence the name Qt gate language and open Qt. You just specify the radix of each Qt in your system. In this case, this is a Qtrip phase. And so you can define new objects very easily. So we can also, this system accelerates numerical instantiation through a very complex system under the hood that I'll very quickly brief over, but you define your expressions and you can build circuits out of this. This is very extensible because this circuit can handle anything that you define using this language. We can then compile that circuit into a sequence of instructions for repeated evaluations. This is unitary and gradient evaluations towards that instantiation process I described earlier. The expressions themselves are JIT compiled with LLVM. There's a lot of optimizations that we do under the hood. We do symbolic differentiation. There's a lot that goes into that. At the very end, we end up with a bunch of function pointers that we can call for these. This thing that we have here on the right is a tensor network virtual machine. At the very end, you can think of it as a black box where you put in values for your circuit, you evaluate it, and it gives you back the result that you asked for. And it does so extremely fast for repeated evaluations. Okay, so how fast? So multi-start instantiation is a very typical operation that we do inside of BQSKit, and we're comparing here open Qtits instantiation to BQSKit. On the left, we have instantiation runtime. So this is how long does it actually take to do the operation. And on the right is success rate. So this is running a full numerical optimization routine. Success rate here is all of these problems have solutions. How many times did the optimizer find the solution? It should be 100%. There's a couple things where it's not because, it's actually a slide. In BQSKit, we're using a very mature library to do this. In OpenQt, we implemented this ourselves. So there's just a little bit of engineering that needs to go in to fix this problem. But in terms of performance, we're seeing a 20x improvement in performance with most benchmarks. These benchmarks are very representative of what we would actually see in compilation, in typical compilation across Qtrits and qubits, both short, shallow, and deep circuits. And the one that I have highlighted here, there's some that are like 100x and more improvement, but the one that I've highlighted and I focused on is because this is the most important, I would say, for the compilation that we do. We typically partition into 3 qubit blocks, and seeing a 20x improvement there is really going to be representative of what we see when this gets integrated into BQSKit. More so that there's no compromises that comes with this. You might think that having an extensible circuit structure like this, where you define your gates, well, there's got to be a price that you pay somewhere. What about when you build the circuit, or when you work with the circuits? That's not true. Extensibility doesn't come at a cost. In this case, I have a constructor for a dynamic time crystal circuit, and I'm defining the gates in the constructor. There's no import from a library. There's no dependence elsewhere. And I then build my circuit using those gates that I just defined, and I can do so extremely fast. I think actually in the latest version of OpenQt, this data is old. I think that number got cut in half. But it's very fast. Compared to BQSKit, I mean, it's miles ahead. So there's a lot of improvement that has happened here. But one thing that I want to point out, that maybe you don't feel the same way about this that I do, but I think this is very cool, is that the gates themselves are defined with the constructor. The semantics of the instructions are attached to the program when they are added to the circuit. If I take my circuit and I send it to someone else, the semantics of those instructions are also attached to that circuit. They don't ever leave the circuit. There's no dependency on an external library or an external definition. With that, when you get the circuit, you can verify that those instructions match what you expect. With that, thank you very much. Everything that I presented today, thank you, DOE, thank you, Nurse, thank you, Chroma. Yeah.